Good day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. I'm a member of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, that is our people, are at the core of our success. Today's webinar is titled Evolution of the Sulfur Block Towards Green Refineries. Driven by sulfur-heavy crudes, continual tightening of product specs, and the implementation of residue upgrading projects, the refining sector is pushing its sulfur processing capacities to the limit. To deal with the increased loads, refineries are installing new sulfur blocks or revamping existing units. At the same time, many refineries are evolving to process ultra-low sulfur renewable feedstocks, which presents unique challenges to the sulfur block. In this webinar, Fluor Fellow Debapam Chowdhury and SME Ayan Dasgupta describe this very important evolution of the sulfur block towards green refineries. Now, to set the stage for today's webinar with the HSE topic, please join me in welcoming Ranjit Mondal. Now, over to you, Ranjit.
Thank you, Dave. Good day, everyone. Today's safety topic is about the prevention of fire in liquid sulfur storage tank. The liquid sulfur product from sulfur recovery units typically contains very low amount of hydrogen sulfide, such that it could be transported, stored, and solidified easily. But upon prolonged storage in the sulfur storage tank, the hydrogen sulfide dissolved in the liquid sulfur can evolve gradually and has the potential to build up concentration even higher than its lower explosive limit of 4%. Additionally, pyrophoric iron sulfides are produced on the tank. Since sulfur tanks are all open to atmosphere, abundance of oxygen can have the potential to create sulfur fire inside the tank. Sulfur fire are not as catastrophic as hydrocarbon fires, yet it has the potential to be very hazardous due to the generation of toxic fumes. Sulfur tank fires are few and far between, with last major sulfur tank fire experienced in 2016 in United States, leading to tank wall rupture and a minor fire. Hence, proper design and operational methods help mitigate and even eliminate the potential of sulfur fire in storage tank. We shall discuss the major design aspect in sulfur tank to prevent sulfur fires. Sulfur need to be maintained in its liquid form. Hence, all sulfur tanks are heavily traced. Tracing is also applied heavily on the tank roof to prevent the formation of solid stalactites. The vapor space inside the sulfur tank need to be well ventilated. A continuous sweeping is achieved by an ejector, which helps to sweep out the vapor volumes inside the tank, thus preventing the buildup of hydrogen sulfide concentration in the tank vapor space. Additionally, any level changes in sulfur tank has to be done gradually, limiting the exposure of the pyrophoric iron sulfide accumulated on the tank wall to the atmosphere. Sulfur tanks are always equipped with proper instrumentation. Analyzer to detect hydrogen sulfide and sulfur dioxide are always provided for continuous monitoring of the vapor space in the sulfur storage tank. Additionally, temperature measurement with alarms are also provided in the vapor space. Typically, the sulfur storage temperature is 140 degrees Celsius, while we set an alarm at 160 degrees C. The escalation of temperature in the vapor space is an indication of localized fire inside the sulfur storage tank. Finally, the liquid sulfur inlet nozzle always kept below the low level of the tank, thus avoiding splashing of liquid sulfur, which has the potential to create spark due to static electricity. By proper implementation of the design aspect discussed here, the potential of fire in sulfur storage tank can be decreased and eliminated completely. Thank you. And with that, I hand over this session to you, Devapam.
Greetings, everyone, and thank you, Ranjit, for your safety topic, which provides a premise about our main topic of discussion today. We shall talk about how a sulfur block is evolving in the present refining scenario and is expected to transform when we might have a green refinery in the future. Crude oils processed in the refinery contains varying amounts of sulfur as its main impurity, which needs to be removed to meet the refinery product quality. Over the years, the sulfur content in the crude oil has been increasing, while simultaneously the sulfur specifications of petroleum products have been gradually decreasing. This means the removal of sulfur from the hydrocarbon phase is extremely essential, making the sulfur block an integral part of any refinery. We shall now provide a bird's eye view on how the sulfur compounds move across the various streams and processing units in a refinery. Sulfur present in the crude oil is in the form of complex compound. The crude oil is fractionated into various distillates. The sulfur also moves along with the hydrocarbon stream. These fractions are typically treated to release the sulfur as hydrogen sulfide. The hydrogen sulfide is captured by an amine which is regenerated to produce a H2S-rich gas. At the same time, the hydrogen sulfide is also captured by process water in all these process units. The sour water thus produced is stripped to produce a hydrogen sulfide-rich gas. These H2S-rich streams are finally treated in the sulfur recovery unit to produce elemental sulfur. So, the sulfur block typically in a refinery complex would include the amine regeneration unit, the sour water stripping, and the sulfur recovery unit. We shall look into each of these units in further detail in the following few slides. The amine regeneration unit receives the rich amine solution. When we talk about rich amine, we mean that it is rich with respect to the amount of H2S it contains. The rich amine is first flashed in a flash drum to liberate any dissolved hydrocarbons. The rich amine is then regenerated in the regenerator column to produce a hydrogen sulfide-rich gas, which is then sent to the sulfur recovery unit and a lean amine solution, which is circulated back to the various processing units of the refinery for absorption of the hydrogen sulfide gases. The sour water stripping unit receives sour water from various upstream units. This sour water is also first flashed to remove any dissolved hydrocarbon gases and is finally stripped of its H2S content in the sour water stripper column, thereby producing stripped sour water, which can then be reused in process. An interesting item to note is that sour water generated in the refinery typically contains equimolar amounts of hydrogen sulfide and ammonia. Thus, the sour water stripper acid gas stream sent to the sulfur recovery unit contains both hydrogen sulfide and ammonia, which needs to be treated. In the sulfur recovery unit, the hydrogen sulfide is converted into elemental sulfur using the modified Claus process. This is a two-step reaction where first the hydrogen sulfide reacts with oxygen, typically sourced from the atmospheric air, in the reaction furnace to form sulfur dioxide. The oxygen supplied to the furnace is just enough to convert 1/3 amount of hydrogen sulfide present in the total feed gas. The sulfur dioxide thus produced in the first stage then reacts with unconverted H2S to form elemental sulfur. The net reaction thus produces sulfur and water from the original feeds of hydrogen sulfide and its reaction with oxygen. It is interesting to note the first reaction is highly exothermic, the second being slightly endothermic with the net effect of exothermicity leading to high temperature in the reaction furnace. This is of interest for the destruction of ammonia. The target reaction is to convert ammonia to nitrogen, which is facilitated by the limited oxygen content in the reaction furnace and by maintaining a high enough temperature in the range of 1250 or 1300 degrees Celsius. Although the main reaction can be summarized simply, the overall sulfur recovery happens across 4 different process blocks, namely the thermal and the catalytic stage, where most of the sulfur recovery actually happens. But since the reaction is limited by equilibrium, complete conversion cannot be achieved. Hence, a tail gas treatment unit is provided. Purification of sulfur produced in the thermal and catalytic stage is achieved via degassing, while to incinerate any unconverted sulfur compounds, we typically have a thermal oxidizer as the final equipment in the unit. We shall see how each of these 4 blocks are functioning in this slide. We start with the thermal and the catalytic section of HSRU. Here, the acid gas is burned in the reaction furnace with substoichiometric amounts of air to generate a mixture of H2S and SO2. Sulfur would start to generate even at this elevated temperature, but would be limited by reaction equilibrium. Typically, at a furnace temperature of 1250 degrees Celsius, sulfur conversion would be around 65%. For further sulfur recovery, catalytic reactors are required, and as this block flow diagram shows, typically 2 catalytic stages are included in design. This would typically recover around 95% of the sulfur. The sulfur produced in each of the thermal and catalytic stages are condensed in the sulfur condensers. The condensed sulfur are sent to the degassing section, where the dissolved H2S and the liquid sulfur is released and recycled back to the reaction furnace. The liquid sulfur is then stored for further processing. Since we could only achieve 95% recovery in the thermal and the catalytic stage, while most modern plants target a sulfur recovery in excess of 99%, a tail gas treatment becomes inevitable. In the tail gas treatment section, all the sulfur components are first converted into hydrogen sulfide in the TGT reactor or the hydrogenation reactor using a catalyst. The reactor effluent is then cooled in a quench column. The H2S is absorbed in an amine solution and regenerated and recycled back to the reaction furnace. In this way, this amount of sulfur is never lost from the process, allowing an almost complete sulfur recovery from the overall unit. Typically, a recovery of 99.9% is easily achieved by this configuration. The sulfur components which are not absorbed by the amine solution in the absorber column is burnt in the incinerator. We now look into the evolution steps of the sulfur block that has been experiencing and is expected to encounter while we move towards the green refinery. In the recent past, the most significant impact faced by the sulfur block was due to the regulation put forward by the International Maritime Organization or IMO 2020. At the same time, most refineries are opting for an integration with the downstream petrochemical complex to increase profit margins. A more recent development of energy transition to process renewable feeds in existing refineries is creating additional and unique challenges to its existing sulfur blocks. And finally, we shall look into a futuristic sulfur block of a green refinery which would process only renewable feedstocks. We start our journey on the path of evolution of the sulfur block by looking at the impact of IMO 2020. The IMO 2020 regulation drastically reduced the allowable sulfur content in the bunker fuel oil or the fuel oil that is being used in ships from 3.5% to a mere 0.5% from January 1st, 2020. This sharp decrease in the sulfur content amounts to an additional sulfur handling capacity of about 20,000 tons per day, which is based on the fact that global pool of bunker fuel oil is around 320 million tons, which are needed to reduce the sulfur content from an average value of 2.45% to 0.5%. While various other means were implemented, like installation of scrubbers in ships to limit SO2 emissions, or the use of LNG as an alternate fuel, yet the major impact was felt by refineries across the globe, as each one of them attempted to manage and process the high sulfur fuel oil stream, thus adding to the sulfur load of their existing sulfur block. A typical example is shown here on how a refinery revamp was planned to manage this. The case study refinery had a high sulfur marine fuel oil as one of the major products, which they would not be able to produce post IMO 2020. As a part of the revamp plan, it is shutting down its existing waste breaker unit, which was mainly designed to produce the required quality of marine fuel oil. The vacuum residue stream would now be processed in the new delayed coker unit, and the heavy gas oil unit, thus generated, is treated in a new gas oil hydrotreater unit. The sulfur compounds which are exported along with the marine fuel oil product would now need to be processed by the refinery as it would be generated from the new gas oil hydrotreater. This refinery actually experienced doubling of the sulfur load after the revamp, and modification in its sulfur block was required to process this additional load. We shall see how this can be managed at a later slide. Integrating petrochemical complex downstream of an existing refinery typically means that the heavier fractions are converted into light distillates, which can then be fed to the ethylene crackers. Hence, some form of a residue upgrade unit is included as part of the design. As the feedstocks for the ethylene cracker need to be very low in sulfur, deep hydroprocessing of this stream is necessary, which again results in multifold increase of sulfur load on existing sulfur block. The evolution towards the energy transition phase of a refinery poses another unique challenge for the sulfur block. Refineries are now including standalone renewable diesel or sustainable aviation fuel units parallel to their existing hydrotreaters, or are revamping their existing hydrotreaters to process a blended feedstock of conventional distillates along with the renewable feedstocks. The renewable source would contain negligible amount of sulfur, thus the acid gas generated would now be leaner in the amount of H2S and would have increased amounts of carbon dioxide. Increasing the inert gas streams in the feed stream to the reaction furnace in SRU leads to lowering of equilibrium temperature, which then has a significant challenge in achieving overall sulfur recovery, as well as creates issues in ammonia destruction in existing sulfur recovery units. We shall now look into an option which can not only help in processing lower acid gas feedstocks in the existing sulfur plants, but also facilitate processing increased sulfur loads. The best way to manage both is oxygen enrichment. Oxygen enrichment is nothing but replacing part or whole of the combustion air that is being supplied to the reaction furnace by pure oxygen. As we replace air with pure oxygen, the amount of nitrogen that is being sent to the furnace gradually decreases. The nitrogen of air actually takes no part in the reaction, only adds to the hydraulic load of the unit and acts as a heat sink, thus reducing the reaction temperatures inside the furnace. So when we reduce the nitrogen content, we can achieve higher reaction temperatures and also process additional acid gases, thus increasing the sulfur load or the sulfur throughput of existing units. Oxygen enrichment is classified broadly into the following three based on the amount of oxygen it would contain in the final air and oxygen mixture. If the amount is less than 28% of oxygen, we call it low level. Anything above 45% is classified as high level, and anything in between is mid-level oxygen enrichment. Since the sulfur block is now facing extreme challenges with respect to increased sulfur loads or leaner feedstocks, high-level oxygen enrichment provides a good method to manage both these conditions with minimum revamp in their existing plant. There are multiple technologies available for a high-level oxygen enrichment, one of them being Fluor's own COPE2 process, which is unique in its sense on the way it manages the escalation of furnace temperatures on high oxygen enrichment levels. A small portion of cold process stream downstream of the first sulfur condenser is recycled back into the furnace using a recycle ejector, which is further described in the following slide. This slide shows the revamp that was done to manage the increased sulfur load post-revamp. The feed gas streams marked 1 and 2 in this slide had an increased flow based on the increased sulfur load post-revamp. The air stream is marked by 4, while a new feed stream was added to the unit, which is oxygen, which is marked 3 in this slide. Since we had a higher load on the furnace and the first sulfur condensers due to the recycle stream that was there to manage the temperature, these equipments were new, as has been highlighted with this specific orange color. The COPE ejector takes a recycle stream which is marked number 6 and sends it back to the burner. This stream is cold, hence reducing the furnace temperature and maintain it in the required operating range of around 1300 degrees Celsius. All equipment downstream of the sulfur condenser would continue to experience a similar hydraulic load as per its existing design. Hence, no major revamp was required on rest of the unit. In this case study, we see how the existing unit was made capable of processing a lean acid feed gas, which is marked by stream 3 here, by utilization of high-level oxygen enrichment. Since the implementation of lean gas was reducing the reaction furnace temperature, oxygen temperature is used in this case to elevate the temperature back to its normal operating value of around 1250 or 1300 degrees Celsius, without any modification being required elsewhere in the unit. The only change that was required was a new burner and some revamp in the existing reaction furnace. As we continue our journey towards a futuristic green refinery, where the feedstock is devoid of sulfur, I pass on to Ayan, who will showcase how the unique sulfur block would look like. Over to you, Ayan.
Devapam, thank you for providing insight into the evolution of the sulfur block in a fossil fuel facility. In the following slides, I'll present how sulfur is managed in a green refinery. Green refineries produce sustainable fuels such as green LPG, diesel, and sustainable aviation fuel from biomass through a process known as hydrodeoxygenation. This process requires hydrogen as an input material. Since these fuels are derived from biomass, their production does not contribute to an increase in net CO2 levels in the atmosphere. Green refineries face a unique challenge in managing sulfur. Although the feedstock itself does not have sulfur, the hydrodeoxygenation reactor where the reaction takes place requires a hydrogen sulfide-rich atmosphere for catalyst activation. Typically, the vapor from the coal separator has a residual H2S concentration of 1300 ppmv. To achieve this, H2S-rich environment in the reactor, dimethyl disulfide, or commonly known as DMDS, is added to the feed. This process results in a gas stream from the reactor with unacceptable levels of H2S and generates sour water. The separation of H2S from the recycled gas becomes more challenging due to its high dilution with CO2 produced during the reaction. Given the small amount of H2S and its significant dilution of CO2, a conventional sulfur recovery unit is not possible. To address this unique challenge, the solution involves recycling and reusing the hydrogen sulfide produced during the process. The overall process scheme is illustrated in this slide. The unit on the leftmost side is the HDO, or the hydrodeoxygenation reactor. This is where the main reaction of converting biomass to green fuels takes place. The unit right of this is the amine regeneration unit. The amine regeneration unit sends lean amine to the HDO section to absorb both carbon dioxide and H2S from the recycled gas. The resulting rich amine is then regenerated in the amine regeneration unit, producing a gas stream primarily composed of CO2 with small amount of H2S and water vapor. The sour water produced from HDO units is treated in a two-stage sour water stripper unit. This unit generates ammonia in a diluted aqueous form and a gas stream having H2S and CO2, which is sent to the H2S recovery unit. The unique H2S recovery unit uses a special amine that selectively absorbs H2S while allowing majority of the CO2 to pass through. The concentrated H2S stream is recycled back to the HDO reactor. The CO2 that slips through the H2S recovery unit has about 100 ppmv of H2S and cannot be directly released into the atmosphere. This gas is burned in an incinerator where the H2S is converted to sulfur dioxide. The sulfur dioxide is then scrubbed with caustic to remove it from the gas stream. The purified gas stream, consisting of CO2, nitrogen, and residual oxygen, is released into the atmosphere. The spent caustic generated is disposed of safely according to refinery practices. This slide illustrates the configuration within the amine regeneration unit, which employs a non-selective amine. This amine has the capability to absorb both hydrogen sulfide and carbon dioxide from the gas stream. The use of a non-selective amine in the ARU is crucial for efficiently capturing these gases, ensuring that both H2S and CO2 are effectively removed from the process stream. This slide illustrates the configuration within the two-stage sour water stripper unit. The first column removes hydrogen sulfide and all the carbon dioxide from the sour water. The resulting gas stream having H2S and CO2 is sent to the H2S recovery unit. The second column removes the remaining ammonia along with residual H2S as overhead gas. The stripped sour water produced at the bottom of this column is sent back to the main process. The overhead gas is then scrubbed with caustic to remove H2S. The ammonia produced is diluted with water to produce an 18% solution of ammonia, which can be used in the selective catalytic reduction of farner's gases. The significance of H2S recovery units become clear as you see the composition of the gas produced from amine regeneration unit. The gas has less than 5% hydrogen sulfide and over 90% carbon dioxide, and the rest is water vapor. Given this composition, the gas cannot be reused unless a major part of the CO2 is removed. The high concentration of CO2 poses a challenge for reuse, making the H2S recovery unit essential for separating and recycling the H2S effectively. As a more concentrated hydrogen sulfide stream greater than 50% is recycled back from the H2S recovery unit, the consumption of dimethyl disulfide is significantly reduced. In fact, DMDS is only needed as an intermittent additive. This arrangement is environmentally friendly and enhances the economic efficiency of the operation. By recycling a concentrated H2S stream, the process minimizes the need for more chemicals, thereby reducing costs and environmental impact. A conventional sulfur recovery unit is not possible for this type of refinery due to the extremely low sulfur content and the high dilution of H2S in acid gas. Therefore, the most effective method is to separate and concentrate the hydrogen sulfide stream and recycle it. By implementing this approach, the refinery can efficiently manage sulfur emissions and enhance the overall sustainability of its operations. This method not only addresses the challenges posed by the low sulfur presence, but also contributes to the economic efficiency of the refinery by reducing the need for other sulfur management processes. This slide illustrates the first stage of the H2S recovery unit, which is used for the bulk separation of CO2. The unit employs a special amine with a remarkably high affinity for H2S, but allowing majority of the CO2 to pass through. In this process, the feed gas is passed through an absorber, where lean amine absorbs most of the H2S, allowing the CO2 to pass through. The vent from the absorber has less than 100 ppmv of H2S. The rich amine from the absorber is then sent to a stripper, where the amine is regenerated. As shown in the figure, the feed gas is having 93% CO2 and only 3% H2S is enriched to 17% H2S in the first stage. The second stage is exactly like the first stage, and this stage enriches the gas to 51% H2S, which is then sent to the compressor. The compressor compresses the gas to H2O reactor pressure, which is recycled to the reactor. Any unbalanced H2S is sent to incinerator. Normally, this bypass line to incinerator has no flow. Lastly, the incineration and SOx unit burns the vent gas, which is CO2 with about 100 ppmv of H2S, to convert the H2S to SO2, which is removed by scrubbing with caustic. The spent caustic is disposed as per refinery practices. I will now hand over to Devapam for the closing remark. Thank you, everyone.
Thank you, Ayan, for the insightful discussion on the unique design that the sulfur block will have in a green refinery. And it is time now to look back at the main highlights of our discussion today. On our presentation today, we looked at the sulfur block on how it is facing a present-day challenge due to the gradual changes in the refinery sector, and it is and as we move along towards a greener future, how it will evolve. In the refinery sector, the sourer crudes need to be converted into lighter distillates to manage the ever-restricting emissions guidelines leading to increased sulfur load. At the same time, we saw that the sulfur load is also increasing due to the fact that the refineries are integrating petrochemical complexes. Simultaneously, as we have started our journey in the energy transition, refineries are attempting to co-process renewable feedstocks. This is leading to the generation of a leaner acid gas stream, again posing challenges in the existing sulfur blocks. we saw how oxygen enrichment can be implemented in the existing sulfur blocks to manage higher sulfur loads as applicable, or manage lean feeds or lean acid gases where renewables are being processed without making any further modification in their existing units. Finally, we focused on a potential design of a sulfur block in a green refinery, processing sulfur-free renewable feeds. A green refinery would still need some sulfur atmosphere for its HDO reactor, and the unique design of the HSRU can be implemented, which can then continuously recycle the H2S to maintain necessary sulfur environment in the HDO without having any need to add sulfur compounds as co-feed or have small sulfur as a product. Thank you everyone for your patient listening, and I now hand it over back to Dave. Thank you.
Right. Thank you very much, Devabham, Ayan, and Ranjit. That was an excellent presentation and certainly very informative for our audience. So we're now going to take just a moment to address a few questions that we've received here from the audience. And for our audience members who have dialed in, a reminder, please make use of the Q&A tab to ask any questions, and that should be addressed to all panelists. Okay, so the first one that I'd like to jump into here is, are there any other methods or design options to elevate reaction furnace temperature in the SRU? And whether Devabham or Ayan would like to take that question, I'll just open the floor and let you jump in.
Thank you, Dev. I would like to take this one. I think that's a very interesting question. Definitely, we only talked about oxygen enrichment as the I think alternate method of SRU, which has the potential to increase the furnace temperature, but definitely that is not the only one. The other options that we have available are fuel gas co-firing, which actually has the potential to increase the furnace temperature while we process lean gases. But co-firing means that we actually increase the hydraulic load of the unit as we add more air to the unit to burn the fuel gas that is burning along with the acid gases. And thus, it is not always the best alternative as a revamp option. Secondly, preheating the feed gases is also another handle, but it is limited by the source of feed. Let's say for SRU, in most typical units, we use 45 bar gauge steam, thus limiting the preheating to around 240 degrees Celsius. For extreme conditions, there are sulfur plants using electrical heaters to heat the feed gases and the airstream to even as high as 400 degrees Celsius. And there is definitely another final thing that can be done. And again, that is another form of enrichment. We call that acid gas enrichment, where the lean gas would be enriched to increase the H2S fraction, reduce the carbon dioxide or any other gas content, thus allowing the furnace temperature to increase. This process is extremely effective to treat extremely lean gases in existing SRUs. So I hope, Dave, I have been able to address the question adequately.
Yeah, absolutely. Thank you very much for doing so. Kindly appreciate it. We do have two more questions that have come in here from the audience. So the next one, and again, Devabham or Ayan, if you'd like to just jump in and answer this one, I'd be happy to hand it off to either of you. And it is this: in green refineries, can we have alternate SRU designs? So over to you.
Yeah, Dev, I'll take this question. This is indeed a very relevant question. The goal here in the green refinery is somewhat different from that of a conventional SRU. Here, the goal is not to convert the H2S to sulfur, but to recycle the H2S to reduce the usage of DMDS. Therefore, any design that can separate, concentrate, and recycle the H2S can be utilized. Hopefully, I have answered the question for the audience, Dave.
Yeah, that's great. Thank you kindly for that. We have one final one here, which I will again throw out to either of you, whomever would like to answer it. And it is this: what are the sulfur recovery percentage in the thermal section and the catalytic reaction section. I think you might have touched on that briefly, but I think the audience member would just like to hear the response to that question once more.
Yes, I think this was discussed when we were talking about the block flow diagram of the SRU. As we saw that the modified Claus reaction converts H2S into sulfur, and it's an equilibrium driven reaction. Higher temperature makes the reaction happens faster, but also it cannot complete the reaction to a higher extent. So in the reaction furnace where the temperatures are high, the extent of conversions are low. So typically we can achieve around 60-65% in the reaction furnace, depending on the concentration of H2S in the gas and various other factors. While in case we have two catalytic reactors, we can actually achieve well in excess of 90%. Typically we target to achieve around 95% sulfur recovery after two catalytic stages. And in plants, typically sulfur plants, older sulfur plants which did not have tail gas treatment, because in those days the sulfur emission specs were much less stringent. So we used to have even SRUs with 3 catalytic reactors, and in those cases we could actually achieve around 98% sulfur recovery in the catalytic stages itself. So again, these are very typical numbers. It would depend exactly on the acid gas compositions and quite a few other various factors. So I hope I had provided some insight into this, Dev.
Yeah, that's great. Excellent. Thank you very much. Now, there's one remaining last minute question that just popped in here. And it is this: is dimethyl disulfide, or DMDS, a continuous requirement in the biohydrotreater? So if one of you would like to take that one, please.
Yeah, Dave, I'll take this. The DMDS addition is actually intermittent, and its frequency depends on how efficiently the generated H2S is collected and recycled. If there is a high H2S sleeve from the system, the frequency of DMDS addition will increase. And the goal for this type of refinery is to collect and recycle the H2S as much as possible and let the sleeve be very negligible, so that the DMDS additions are highly intermittent, because it's actually a foreign product, costly, environmental problem, and we don't need more DMDS to be added to the system. Thank you, Dev.
All right, very well. Well, those are all the questions I'm seeing coming in here for today. So we will work to close. And again, thank you to Debapam, to Ayan, and to Ranjit for what I call a really informative webinar, and certainly the time that you've spent both today in presenting and in preparation leading up to today's event. I'd like to also thank you, send a thank you rather to our audience for attending today. It's certainly been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on Fluor.com, or also following our social media channels using hashtag Innovation Builders. If you'd like to send us your email notifications for future webinars, you can certainly email us at innovation.builders@fluor.com with opt-in in the subject line. Again, we appreciate your attention and thank you for dialing in today. We will send out a compiled list of the Q&A shortly, along with the notification that the webinar recording is available for replay on Fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day, and thank you very much.